Yeah. Okay. So if unification. Yeah. So if the predicate matches, if the entities match and the name matches. Yeah. And two constants match if they are the same, if they are identical, and a variable and bounded variable and a constant match if the bounded variable and constant has the same value, and a bounded variable and an unbound variable match always with the unbound variable bound to the value of the bound variable. Yeah, is that clear? Whatever the rules of unification were, I hope it is clear. I mean, we did it last time. Okay, now let's see. Let's be very precise about how Prolog works. Okay, so Prolog works by unification. Unification is the basic this thing, and then basic strategy, and then it goes on to derive the empty query. Now, how does it go? So if I'm given the input to the Prolog algorithm is a query queue, okay, and the query queue is what we have to evaluate. And if the queue is empty, if the query is empty, then it means that it's going to be a recursive algorithm. I'm going to supply a query, and the Prolog is going to work a recursive algorithm. At the end of the recursive algorithm, if we are able to derive the empty query, then what we are going to output to the screen is all the bindings we have achieved so far, all the variable bindings, because that's the computation we have performed. That's the purpose of the computation, to derive these variable bindings. Okay. So if queue is empty, then it means that the query answering has been successful, and we print bindings of all variables in the original query if the user wants. If the user wants more solutions, that's when we enter the semicolon. In which case, we return false, else return true. Okay. Now, if the query is not empty, then we remove the first predicate from the queue and let q1 be this predicate. And for each rule, r is equal to h if r1, r2 up to rj in the program, in the order they appear in the file. Okay, so we are going to take each rule in the program. Yeah, so we are considering facts also as rules. Okay, facts are nothing but rules with an empty premise. If H unifies with Q1, i.e. the head of R unifies with Q1, put each Ri into the query Q so that if the Q was originally Q1 to Qk, it now becomes R1 to Rj, comma Q1 to Q2 to Qk. So that means that we have taken this query Q1 to Qk. We taken the first one Q1. We see if this Q1 matches with some of the rules in the given program. If it matches, we take that premise of that query, that rule, that is R1 to Rj, and then we attach it to the current query. We have seen this example of this one before. We are just repeating it. Yeah. Rules body is put in front of previous query predicates. Also, some of the variables in our RIs and Q2 to Qk might now become bound because of unifying H with Q1. Okay. If evaluate Q, now we are recursively calling evaluate function on this updated Q. Okay. So they should actually use some other name for maybe Q prime. Yeah. Recursive colon updated Q. And now you recursively call and you return. Okay, so if the recursive procedure is over, if it succeeds, then it comes back to return. Yeah. So when does that recursive call succeeds? It can happen in two ways. One is it with the current rule, you have updated the query with the current rule, and it goes. It might finish, it might not finish, but when it comes back, what it means is that we have to try the new. We are inside this loop, for loop. We try the new uh, rule. Yeah. Else, undo all the changes to the variable bindings that arose from unifying H and Q. It's written in M. Okay. And this is the end for the end of the for loop. One second. For each rule, you evaluate, you update the bindings, and then you call, and when it comes back, printed bindings and recursive call. Okay. All right. Any questions? Questions? Did you understand this? Probably not. Let me try once more. So we are inside recursive call, evaluate. Evaluate takes a query, and if the queue is empty, that means that we are at the bottom of a recursive call, and we print everything, and then we just return. Okay. Otherwise, what we do is that we take, for each rule in the program, we update the query, and we recursively call evaluate on the updated query. And once it returns, it means that we just have to go back. So we return. Otherwise, we undo all the changes to the variable bindings that arose from H and Q1. Okay. I mean, if you think about it, I think it will become very clear, because right now it's not written in a nice fashion. Okay, let's move ahead. All right, I'll leave it to you to figure it out. It's not a very complicated thing. Yeah, question.
Sir, I had a doubt.
Yeah.
Yeah. Sir, on the slide, can you go back 2 slides?
Yeah.
Yeah. One more, I think. Huh. On this slide, you say that we print if user wants more solutions and enters semicolon, then we return false. What is this doing actually? Are we saying that since queue is empty, there are no other alternative solutions possible?
Uh, if queue is empty, so what happens is the following. One second. Yeah, if the queue is empty, it means that there are no more solutions. Yeah, so you have to think of it this way. Um, One second. Actually, I have to think about this. All right. I don't have an answer at the moment. I have to think
Uh,
about
so
it.
if it actually returns false, then it'll just go backtracking back up to find the next true value, which is
Yes,
what we want in the semicolon.
yes, that is true. But why? Ah, ah, yeah, Siddharth. Yeah, thanks, Devyani. So what this return false is the input to this if statement. Okay.
Okay, so the function that called it previously, that understands that the previous on this branch I have no solution, like that.
This false and this true are not the one which is being printed. This one just means that if you want semicolon, then uh, I need to go back and start search again. Yeah.
Okay, sir. It just means that this branch has no more solutions then.
Tell me again once more.
So,
If this
so
branch, if this branch has, no, one second. If this branch
So the
has,
query is empty, so it can't go ahead.
so we you have to imagine that we are in the middle of some procedure call. Okay, that is where we yeah, it can go ahead. That is true. That is true. If the user wants more solutions, then um, hello.
yes, sir.
Mm. Okay, so what happens is the following. So you start with a query queue. Okay, now uh, that recursive call is going to call another one, another one, another one, another one, another one, till it reaches the empty query. Okay, once you reach the empty query, you print all the bindings, and then you wait for the user's input. If the user inputs semicolon, that means that I need to go back and search for the next query. Yeah, for the next possible solution. On the other hand, if the user does not print that, then all what can we can do is that we just return the function one after another. So it goes back to previous one, goes back to previous one, goes back to previous one, and goes back all the way to the function who called evaluate queue. Okay, so that procedure call is finished. Otherwise, what happens is that you return false. So it goes back, the variable bindings are undone all the way up to uh, the evaluate queue function, and it takes the next for item and continues. Is that clear, or does it make sense?
Yes, sir. Now it's clear to me.
Yeah, so this false is coming back here. This false is coming back here, and if it is true, then the function will return. Yeah, so this is a place where a lot of recursive calls have dispatched. The first one, starting from the first one, it has come here, and this is the one goes in recursion, and it comes back here and it returns here. Okay, if false is returned here, then or undo all the changes to variable bindings that arose from unifying h and q1. Okay, and then you start searching for a new solution. Okay.
Yes, sir. I got it now.
Yeah. The procedure operates like a depth first search, where the order of the search depends on the order of the rules and the predicates in the rule bodies. When Prolog backtracks, it undoes the bindings it did before. Yeah, so you can see that the previous algorithm is just like a depth first search, where the nodes of, you can think of that Prolog program as a graph, where rules are where the rule heads are individual vertices, and you can think of it as a hyper graph. Yeah, a hyper graph is a graph with normally your simple graph is a graph with every edge connects between two vertices. Yeah. Now a hypergraph is a graph where an edge connects between two or more vertices. Yeah, more than two vertices, for instance. So you can think of a rule as a hypergraph. It connects this vertex to all these vertices simultaneously. So you can think of normal graph, you draw the arrow edge like a line. In a hypergraph, you can think of an edge like a spider. Yeah, so you have the one vertex and then it connects with so many other vertices. Now, the Prolog program is like a DFS search program, exploring the DFS search program on a hypergraph. Okay, if you think about it that way. Okay, and yeah, let's move ahead. Okay, so now I think we are at a position where we can answer this question, which we saw it in the last class. I have a graph, edge AB, edge BAC, edge BD, edge DE. And if I write path like this, path of xy, if path of xz and path of zy, and I have the next rule, path of xy is edge of xy, then this does not terminate. Yeah, it goes on infinitely. Why? Somebody could answer me now. Why doesn't it terminate? The reason why it doesn't terminate is because if I am given a query like path of AE or something like that, then what happens? Path of AE, X is bound to A, Y is bound to E. And then in order to prove that, I have to take path of X is equal to E and Z some arbitrary value. And I try to unify path of A and Z with some rules. And the only rules which I have is these two rules. And again, I come back here, I unify path of A and some Y, and then I go into again this rule and so on. So I continue there. Yeah, I continue in the first rule, first predicate, and it's an infinite loop. That's why it doesn't terminate. Yeah, on the other hand, path of xy is edge of xy, path of xy is edge xz, path is zy, terminates. Okay, because here I have the facts first. All right. Runs. Okay, I think that we have seen this. Not on Prolog variables. Prolog variables do not operate like other programming languages. You cannot change the value of variables. Once they are bound to a value, they remain bound. However, if a variable binding contains another variable, that other variable can be bound, thus altering the original variable's value. What it means is that if I have a variable which is f of a, g of y, and y is equal to b, then x is also bound with y's value substituted in its value. Yeah. So x will become f of a comma g of b, and y is bound to b. Yeah. So the scope of an Prolog variable is given for the rule. I mean, you should not think that because I use y is appearing, x and y appears here and here, it means that this y and this y are not the same. Yeah, scope of a variable is within a rule, and scope of a constant is throughout the program. So if I mean a here, throughout the program a is this a, because it's a constant. But on the other hand, if I have x and y variables, then this x and this y is only within this rule, and this x and y is only within this rule. So when I take path of xy and path of xz, and next time when I come, when I take path of xz, this z, this y is a fresh y, yeah, which has the binding as z. Is that clear? It's not a, I mean, it behaves exactly as your intuition tells you. Okay. Okay. All right. Now let's come to list processing. Much of Prolog's computation is organized around lists. Two key things we do with a list is iterate over them and build new ones. Checking membership. Okay, I have here. So if I want to, I already told you last time that list, if I want to define member x underscore, this underscore, so here what it means is that I'm stating a fact. X is a member of the list which contains x as the head. And underscore is any variable whose value we don't care. We are not reusing. So if a rule contains underscore at 3 different places, these 3 underscores are different things. Okay, they can stand for possibly different things. So here it means is that I don't care what is this value of this second variable is. So I put underscore there. So it's either called wildcard or anonymous variable. So x is a member of x, comma, x bar underscore. Similarly, member x is a member of underscore bar t if x is a member of t. So here I don't need to care about this first value, because I have already a rule which says that if x occurs in the first element, it is already satisfied. So that's why I'm leaving this first element. I can understand that if I am ever coming to this rule, already the first element I have possibly checked if it is to be x, because if it is x, then it is already satisfied by the first rule. So when it comes here, I don't need to bother about this first value. And I can just say that member x is a member of this list if x is a member of t. Okay, now if I say x is a member of 1, 2, 3. Okay, x is 1, 2 as well as 3 are members. What if we define members like this? Member x underscore member x yt, x not equal to y member xt. So what if you define it like this? You say y here and x is not equal to y member xt. And then x is equal to 1, and then it says false. So only for x is equal to 1 it is true. And that x is equal to 1 is because of the first rule, because when x is equal to 1, then 1, 2, 3, member 1, comma 1, 2, 3 is satisfied by the first row, and that is given as an answer. But for others, it does not work. And the reason is because of the negation operator. Yeah. So we have already seen that we never talked about negating a predicate. Yeah. The procedure which Prolog operates, the recursive call which we have seen, in which case in that what it was trying to do is that it was trying to prove something. We have never tried to. There was no clause which said that X is how to disprove something. Yeah, here what it says is that the meaning we have in mind is that this second rule is true, X y t, if X is different, there is some Y says that X is different from Y. If Y is different from X and member of XT. Yeah. Now to understand what is going on here, we need to understand what is this meaning of this operator. Okay, we'll come to that later. This is known as negation as failure. This is same as writing plus X is equal to 1. I should put a bracket. Yeah, this is same as putting a bracket. This operator, we'll see this operator. Negation as failure. Okay, we will see that in detail what it means. What it means is that NAF means that negation in Prolog is failing to prove otherwise. Yeah. It is so. For instance, it's like a court case. Yeah. Just because in a court case, Prolog is like a court in which you are trying to prove somebody is guilty. Okay, if you are able to prove that somebody is guilty, then he is guilty. It's just like in Prolog, you are trying to prove something is true, and failing to prove that it is true doesn't mean that it is false. So yeah, in the court scenario, it is like failing to prove somebody is guilty is not same as saying that somebody is innocent. It just means that you are failing to prove somebody is guilty. Yeah, similarly, negation as failure is different from negation because you will never be able to, in Prolog, you don't have the means to say that something is not equal to Y, because we saw that our trying to prove something is by trying to unify. So when you are trying to unify with something, well, all what you can say is that if I'm failing to unify with all the possibilities, then I can say that and then I can assume that it is negation of that what I was trying to prove. Okay. So in this case, why it becomes that if I'm trying to prove member of X and the list 1, 2, 3, where 1 will become Y, and I am trying to prove that X is different from 1 and member of X comma T. Okay, let's come back to that later. because it's going to be complicated.
Sir, I have a doubt.
Yeah.
So why did we in the first place introduce that negation there?
No, this is
So when
because,
when we replaced the underscore with y,
yeah.
so why did we at that time introduce that negation predicate?
Because you see this program has a deficiency, which is that the order of these two clauses are important. You cannot switch the order. Okay. So if you put this rule in the beginning, okay. No, it will still work. It will still work, but when we are trying here, when we write this, we don't care about the value of the first variable. That is because we say that the value of first variable, the value of the first element, list element, is already captured by the first rule. Okay, x being same as the value, x being same as the first element of the list, is already captured by this first rule. Therefore, we don't need to care about that. That's how we wrote the second rule with the underscore in the first variable. Now, when it came, now if somebody asks you, can you write so that these two rules are disjoint? Okay, and you can shuffle the rules. Then you need to say that the first element is different from x. If the first element is different from x, then I will search in the rest of the list. Okay.
So, but that thing is anyways checked in the first rule itself. So even if what I think is, even if we remove that particular predicate of
Yeah.
negation, then
Yeah.
also shouldn't it work?
Yeah, it will work. It will work. There is no doubt about that. It's not a good example, but there are predicates where though you cannot shuffle. If you shuffle, it won't work. Okay, we can try to find such an example. There the just to let me see. So, for instance, if I want to say that two lists are disjoint, okay, or two lists don't have a common element, yeah. Let's imagine I want to define something like minus list minus x L1 L2, okay, and I want to say that x is an element of L1 but not an element of L2, something like that. Okay, so I want to say that x is an element of L1 but not an element of L2. Now, in this case, I cannot do without there is no way I can write this program without negation as failure, because I want to say that x is not an element of L2. I cannot prove that x is an element of L2. Okay, so this I cannot write without negation as failure. But in this case, you can always write it as a negation as failure, but that's why I said it's not a good example. And there are plenty of such examples where you have you need negation as failure. Okay. Yeah. Let's first write some list programs, and then we'll come back to this negation as failure.
So,
Yeah.
how do we show an empty list in Prolog?
Just square bracket. So let's do an example. Let's do size list size. Okay, so list size will be empty list will be 0. List size underscore T underscore bar T N will be, can somebody tell me? Yeah.
List size T plus, no sir.
So first I want to say that
N1 equals list size of T.
yeah, list size T N1
And N1 plus N equals N1 plus 1.
N is N1 plus 1. List size and you get x is equal to 4. Okay. All right, that's here. The size of list is 0. Size of list size is N1 plus 1. This is just computing the sum of a list of numbers, sum list. This I think you will be able to do yourself. Let's do this one. Implement append L1, L2, L3. Append is a very important operation. Okay, it has the same status of fold in most of the functional programs. Append is very useful. Append L1, L2, L3, which holds if L1, L3 is the result of appending the list L1 and L2. For example, append of ABC 1, 2, 3, 4 is ABC 1, 2, 3, 4. Can you try to write append? Please try. Append L1, L2, L3 is true if L3 is L1 plus L2. How do I write append? What should be the base case? It's again recursive. What should be the base case?
If L1 is empty, like
Yeah, if empty list L. Yeah, if the first list is empty and the second list is L, then the third list is also L. Now, if the first list is X bar T and the second list is L, L, and the third list is L3, then try. Maybe I can write it like here. Yeah, yeah, I will try that later. But first you tell me. I mean, I have written X bar T because here we have taken empty list as a base case. So the next in the recursive case, it will be X bar T. Append
T comma L2 comma L
11 o'clock.
T comma L2
comma L
comma L
and L3 equals L3 is X dash L list dash L.
That's right. Yeah. Yeah. So basically, instead of this, whatever you have written at the end, I could just say append of L, L2, L3 and come here and say X bar L3. Yeah, because unification works both ways. So append of x t L2 x bar L3 will be append of t L2 L3. Yeah. So you get ABC is 1, 2, 3, 4. Okay. Now, what is last x L? Last of a list. X is the element of last of a list. If now let's try to write some functions using append.
Sir, actually, I have a doubt.
Yeah.
So in the above, the both the x's are interpreted as the same thing, right?
Both the x's are not independent. The scope of a variable is
So
uh,
they're the same x, right?
yeah, it's the same x.
Okay.
Scope of a variable extends to the entire rule. Okay, so if I have an x in x somewhere, it should mean the same x in throughout that rule. Okay, except underscore. Underscore has does not have the such a scope. So if I have two underscores, it can mean two different things in the same row. Okay.
Okay, sir.
Yeah. So how do I say that x is the last of a list? So I can write it as append. So if I append x to no, 1 second. How do I say last of a list? No, this is, I don't know. This is, oh, no, let's try something else. Okay, let's go to the second slides. Then we'll see policy. Um, let's debugging and all we can do later. Yeah. Okay, so this is what we have done append. We'll come back to debugging and all in the next class. Okay, so now it's not append here. Let me see. Let's try to do some. Yes. Okay, anyway, let's try to. I don't know if last can be done using append. Think about it. But anyway, let's do last of a list. Last of a list, XL. So last of a list which contains X is X itself. Last list X underscore T will be last of list of last list of
X, comma T.
X. Yeah. Let's try to do some examples. Can you try to do reverse? It is try to do reverse. Let me see if I can find. Let's try to give some exercises. Um, Subsequence. It's going to be. This is going to be tough, huh? Subsequence of X is a subsequence of Y. What do you mean by subsequence of a list? Sublist of a list. I can take the original list Y, cross off some of the elements, and what remains is X. Okay. Um, yeah. Subsequence. Reverse. X is sorted. Now, this will require negation. Excess. Okay. Maybe I should put it at the end. Or is a star. A bit of difficult. Okay, in the next class we will see negation as failure and cut, and by next week we will finish off prologue. All right.
Sir, I had a doubt.
Yeah.
Sir, in the program you wrote of that, uh, mm, uh, yeah, in the append. So in the append, when we first call append, the third argument it sees whatever the third argument is, it tries to bind it with x L3. So doesn't it pose a problem because it tries to look at the first element of the first argument and the first and that x to be the same x as this, and which in this case is not true.
Actually, I didn't understand your question. Can you be a little slow?
Okay, when we call append with uh, three lists, so we give L3 as a empty list when
Mhm.
we call it, right?
No, we didn't give L3 as an empty list. No. To append, no, I just gave it as a variable x. So here I gave x as a variable.
Okay. So, sir, what I was asking is that it doesn't it try to like split that variable and compare the first element of the first list and this, and why doesn't it fail then?
No, when I give x, what happens is that there is a variable binding which will be created for this call, and that will be passed. And when you call that second L3, this L3 is a new variable. So this is not, Prolog does not see this as a split variable. It just sees it as one variable whose value I don't know. This x is unified with this expression. Okay, and the first element of that expression I already know from the fact that uh, x is given a here. Okay, so now it tries to prove append of a t L2 L3. And once I get L3, I know what to do to get this x back. Does it make sense?
Yes, sir, it does. But
I
so
yeah.
actually, just for the sake of clarity, if we consider the third argument of append as y,
Mhm.
so what it does is it tries to it creates a binding of y with this x L3,
Yes.
and what I'm saying was that won't it try to, okay, so you are saying that it will take this x from the first list itself.
Yeah. Because that binding is already created. Because there is no way I can unify this append with the first rule. So I'll always take the second rule. Now, when I take the second rule, x bar t means that x is A and t is BC, and L2 is 1, 2, 3, 4. And therefore, this y is x bar L3. So the first element is A. So now I'm trying to unify a append of t and L2 and L3.
Okay, sir, it's clear now.
Okay, so try to do this, and next week we'll do negation as failure. You can you can go through this slide once this second slide. That will make our life easier. And because there are this list reversing, I think you will be able to do yourself, because we have done it in the case of Lisp. This kind of off and square reversal, off and reversal, and this Fibonacci and all is also the same ideas which we have seen in Lisp. Okay, but the point is that the code looks the same, but what goes on behind the screen is very different. Yeah, that's very specific about Prolog. Unlike in the functional case, what goes on behind the screen, even though the code looks exactly the same, most of the Prolog programs, if you just translate, it will become Haskell code. But what goes on behind the screen are completely different things. Okay. All right. So I hope you will be able to read this far had come. Okay. And we will try to do n queens, and that will be our finale. Okay. Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.